So for today, we'll be discussing circuit applications, but these are both the standard and the simplest fundamental application of differential equations for circuits modeled using, of course, differential equations. Before we go to the real DE, let me first show to you the circuit elements that will be present in the circuit later on that we're going to model. So what you see here in the first picture is a resistor. So this one is a resistor, smaller version, and we have here a bigger version. Sometimes they are placed in this particular kind of block where they're inside this particular resistor. So the coin there is just a reference to you on how big these resistors are. In your physics, high school physics, and in your physics when you were in first year, you have seen that a resistor has a symbol of this one. And this is your current I passing through this particular circuit element we call the resistor, and in the process having a particular potential already. So this particular element has already a potential difference due to the passage of the current to it with this particular voltage. So now you get to see that the voltage is equal to the product of the resistance and the current I. So in your circuits, this was already discussed to you that the unit for voltage is rather, yes, it's in volts. The unit for resistance is in ohms with this symbol, and the unit for current is in amperes. So if we are going to connect the current with the resistor, what we'll have is the voltage. The voltage across the particular, let's say, circuit element we call the resistor. And specifically, class, with this formula, we are computing for the voltage drop in this particular circuit element. Now, the circuit element next that we're going to discuss is the inductor. Wait, Kasha. Okay. It's the inductor. So these are inductors, sample of inductors. And in your circuits, you get to see this particular symbol representing the inductor. And the voltage drop across this element is represented by V with the subscript L. And the current passing through it is I with the subscript L again. So for our inductor, the voltage drop is equal to the product of the inductance in Henry. So the unit for inductance is Henrys with the rate of the change of current over time. So this is the derivative representing the rate of change of current over time that is passing through the circuit element we call the conductor. If you're going to multiply that to the inductance in Henrys, that should give you the voltage drop across the circuit element. Now notice that this time your voltage drop is already having the appearance of the derivative. And as such, later on, when you're going to set up the differential equation, then you have already the derivative's presence. The d sub I dt is the rate of the change of current, and since it is the rate of change of the current, the unit is expected to be the current unit over time in seconds. And by the way, when we do circuit analysis, our time unit is always in seconds. Now note that the voltage drop across the inductor is equal to 0 when the, shall I say, the inductor is acting like a short circuit. So V sub L is equal to 0. In this case, inductor acts like a short circuit. When I sub L is a constant, meaning there is no change in the I over time that passes through the circuit element, then your circuit is said to be a DC circuit. You know what a DC circuit is. The power source is a battery. So there won't be any changes in the current once your circuit is powered or having a potential source, which is a battery, or it's a DC circuit. Now, the last element is the capacitors. These are examples of capacitors, and they have different colors. Something to do with their, of course, capacitance. Now, the capacitance unit, as discussed in physics, is farad. And the Q, now we have this new circuit unit, which is the coulombs, representing the charge in your capacitor. So the charge in the capacitor Q is equal to its capacitance in farad multiplied to the voltage drop across your capacitor. Capacitance in farad multiplied by the voltage drop across your capacitor is the charge on your capacitor. Now, the current passing through the capacitor could be represented by the rate of change of the charge that is in your current at a particular time, or how does the charge in your capacitor rather is changing over time. Okay, the charge in your capacitor changing over time, and that's your current. So rate of change of the charge, again, the charge being in coulombs, and then the unit of time, which is in seconds. Now, our I, in this case, if we go back to the main derivative represented by I, if we change the Q in the dq in the numerator to the product of the capacitance and the voltage, that would be this one. And since capacitance is fixed, it's the rated capacitance of a particular capacitor. When you differentiate, the C is placed before the derivative, and you have already dV/dt in here. So the dV/dt is the rate of change of the voltage, which is of course volts over seconds. Now, your I in your circuit having the presence of a capacitor can then be represented or replaced by C dV/dt. Okay, that way your circuit, when represented in terms of Ohm's law, wherein you sum up all the voltage drop across your circuit and equate it to zero, you will have already the presence of a derivative, because if you're not going to replace I with an expression which has the presence of a derivative, then when your model later on will not be a differential equation. Okay, so this is the replacement of the I. Now, note that I is equal to 0. And when is this? When your capacitor acts like an open circuit. So actually, it's just like this one in your inductor. Your VL is 0 in the case of your inductor when your circuit is a short circuit. It's like a short circuit. This one, your current is 0 when your capacitor acts like an open circuit, with V being kept constant. Now, we will only limit our circuits here in DE to the two types having those elements mentioned. It could be a it could be a resistive circuit in this case, and a capacitive circuit because you have the inductor, or you have this one, a resistor only. So you have an RL circuits here, and you have here an RC circuit. RL, resistance and capacitance, or rather inductance, and this one is RC, resistance and capacitance. So only types of circuits. Now, we will not anymore discuss for now RLC, wherein all these three are present, because our circuit would be now modeled using a higher order differential equation. So we will only take two at a time. So the R and the L, one type of circuit, and the other, the R and the C, for another type. So we will not have all three, because the result, as I've said, will be a higher order DE. Now, this particular electrical potential E here could be 0, or it depends on the problem on what is this particular electrical potential. It could be a constant in the case of a DC circuit, or it could be having expressions of sine and cosine if it's an AC circuit. Now, if it's not present, then you have a case of a circuit which does not have any source. Okay? Now, we will go to those samples later on. Now, the basic equation governing a circuit which has the inductor and the resistor is the one that you are seeing here. So you have the current I in amperes, and you have here a circuit which has an electrical potential of E, represented only by E. In some circuits, this is, as I've said, in terms of the sine and cosine function, and some it is a simple constant in the case of the DC circuit. So for an RL circuit, your circuit is in the form of a circuit first order differential equation which has the unknown function I, which is the current, and the independent variable time. The R and the L, the E and the L are most of the time constants. So R is a constant, the resistor, the resistance, and L, the inductance, is also a constant. But the E at times is a function of time. So if that is the case, then we will have a little bit of a challenge because the challenge always is in the form of the E. But if this is a constant, just like the R and the L, then we have a very simple differential equation. It will only be complicated if the E is a function of time. Now, if it's an RC circuit, the one that has the capacitor and the resistor, so where is that? This is your capacitor and you have this resistor here. Your DE would be something like this. So, by the way, these differential equations are using Ohm's law, Kirchhoff's law, of summing up all the voltage drops in your circuit and equating them to zero. Okay, so we have dq dt plus q over RC being equal to E over R. We will not derive anymore how this became, but from the basic law in physics, but rather we will concentrate on these two differential equations that we'll be using. And it's easy to know when you use one because it's really apparent that in the first case, you have resistor and inductor. In the second case, you have resistor and capacitor. And again, there is this emphasis I placed here that in here, your I is the derivative of Q with respect to time. Now, this circuit here, equation, the second circuit equation has the unknown function charge in columns for your RC circuit and the independent variable, which is time. Okay, so it depends really on what are the given in the circuit on how will your final differential equation would look like. But if you're going to ask me what is really very important is that you get to know these two differential equations that will represent your particular circuit. That's just how simple it is. So this one is for RL and this one is for your RC. The rest would be all about the mathematics on how to simplify these particular circuit equations. Okay, now as for our sample problem number 1, we have here a source-free RL circuit. So this is what I've mentioned a while ago, which doesn't have any electrical potential. So it does not have any constant electrical potential and it does not have any, it's not an AC circuit wherein the potential difference is as a function of cosine and sine. It's a source-free RL circuit. So you have the resistor and you have the inductor, the current I, and you have the voltage drop across your resistor, which is V sub R, and the voltage drop across your inductor, which is V sub L. According to what you've learned in physics, you need to sum up all the voltage drop in your circuit element and equate it to zero. That's a very standard principle in circuit analysis. Now, as to the voltage drop across your inductor, it was discussed a while ago, the voltage drop across your inductor. This is the voltage drop across your inductor, the L over di dt. So we're going to place it in here, and you have L di dt. The voltage drop across your resistor is R, the resistance, times the current I. Then this is equated to zero. If you look very closely at this could be a linear differential equation, or it could be a simple separable differential equation. It could be linear if you view your Q of t on the right side being zero. But as I have written here, it is simpler considered as a separable differential equation. So what you could see here, the entire equation here was divided by the inductance to come up with a separable differential equation, which is di dt plus R over L times I. Now, if you will divide the entire equation by I and multiply it by dt, you get to transfer the dt here in the derivative and the I here in the second term below. So now you have transferred I in here by division, and you have transferred the dt on the second term by multiplication. Okay, so this is now your DE. And then since it's separable, if you look closely, all you have to do is integrate. So you integrate this first term from initial current to current after a particular time. This one will be integrated from 0 time to time, whatever is the time would be. That would be generic, that we can only substitute later on if we are already given the time elapsed for our circuit. Now the R and the L, the resistance and the inductance are all constants that we can readily substitute. So we will simply actually integrate di dt and dt. Now, since in circuit analysis, we already have the C representing the capacitance class, we will not anymore use C as the arbitrary constant. We will use the constant K representing our arbitrary constant of integration. Now, you don't need to write this one if you have limits already substituted here, actual limits. But if there aren't any limits, then you have to write your arbitrary constant C, which is supposed to be ln C, as ln K. Again, because we already have the C representing the capacitance. So this is our circuit for this source-free RL circuit. So this is our, what did I say? This is our model DE for this source-free RL circuit. This is your model DE. In itself, it's already a differential equation. Now, if you integrate, you have an ln of I. If you integrate, you have a t and you have an ln k. And you have this. If you use the, if you will transfer the ln that you have here on the right side, on the left side, you will have this. And this r over L times t on the right side, that would make it negative. Using the properties of ln, so you will have ln I over k equal to negative RLT. Then if we'll make the entire equation left and right side the exponent of the E, we get rid of the ln on the left, so that would be I over k. And what we have on the right would be an E raised to negative R over L times T. Now this is an equation. Now there are questions related to problems on circuit applications that are really shall I say, connected to terms that refer to specific values. So this equation allows you to determine the natural or transient response of your RL series circuit. So if the question is asking what is the transient response or what is the natural response of the RL circuit, this would be your equation. All you need to do is substitute the given initial conditions, 0 for times initial time and I sub O for initial current. So if you place this one as I sub O and this one would be 0, this would be E raised to 0, which would be a 1. That gives you an I sub O equal to K. So now you will replace the K here in our equation as I sub O. The rest are copied. So the current, the transient response in your circuit given the time and the initial current passing through all circuit elements will be computed using this equation. Knowing the time, and it should be in seconds, and knowing these constants, resistance, inductance, and initial current passing through the circuit, you will be able to determine the time in your RL circuit at any particular time. Okay, so the current will be solved given the time, okay, as long as the time is in seconds. If this current that you have, that is written in this equation, is plotted against time, as you could see here, the response is exponential decay. You could see the value of the I decays as the t increases. Okay, so in that case, since it's decreasing over time, we expect that if the problem is saying what would be the current after a very long time, So take note, what would be the current after a very long time? That would be similar to asking what would be the current when time approaches infinity. After a very long time is t approaching infinity. So you will substitute infinity here and you will have an e raised to negative infinity. E raised to negative infinity class is 0. And anything raised to 0, whatever the value of the initial current here, would also be a 0. That explains this curve here. Over time, as t approaches infinity, meaning it's increasing, the current will approach the value of 0. This one is 0 current, okay, as plotted in here. So that's in the case of your RL circuit. Now, there is this what we call time constant in circuit. And that time constant is the ratio of the inductance with the resistance. So you divide the inductance with the resistance. That should give you the time constant in seconds. Again, the time constant is seconds. What is the significance of this time constants? It tells you in seconds how long will the current from its initial value drop to 36.8% of its initial value. So if example lang class, example, if the initial current is 100 amperes, the time that you have computed in seconds using the formula L over R tells you that that would be how long in seconds will the current be reduced to 36.8 amperes from 100. That is if we start with an initial of 100. So it could be, you should know this, it could be something that would be asked by the problem also. Like, when will the current be 36.8% of its initial value? If you did not know this concept, then you didn't know that actually it's just the ratio of the L and the R. So all you have to do is divide the L by the R, and that gives you the time when the current, initial current, drops to 36.8%. We refer to this time as the time constant, and it's always in seconds, just like all the time values that we are substituting in our circuit applications concerning, of course, RL, RC, and all the other circuits. Okay? Now, if there's a question like, can we use this, Miss, as our, I read this one, can we use this as our, shall I say, standard formula for an RL circuit? As long as your RL circuit is source free, meaning it does not have any potential difference. E here is 0, that is why it's equated to 0. Then you can use this formula. If we have an E, there will be a constant here or there will be a function here in time, then this particular formula derived will not be anymore used. But your time constant would still be L over R. That does not change the fact that this is the time it would take for the current in the circuit to drop to 36.8% of its initial value. And the equation that you will be coming up later on for the I, wherein you don't have, wherein you have, let's say, an electrical potential difference, it's not 0 here, would still be what we call the transient response of your RL circuit. Meaning this equation that was derived for you here is only for a source-free circuit. Okay? Now that's for the RL circuit. Let's have another sample for this one. Before that, do you have any question here on the RL circuit? Do you have any question? I will upload this later when we're done. Okay, the document and the recorded discussion. So I will be disconnected because I have less than a minute. We will just click again the link that I have provided. Okay, so I will read the problem. Number 2, if there aren't any questions. If the inductor has a current, so still on the RL circuit, 2 amperes at time equal to 0, so meaning this is your IO, find an expression for IL valid for t greater than 0, and you find its value, the I, referring to the I, at t equal to 200 microseconds. That's our problem. Initial